Yeah. So let me start then. Okay. So good afternoon. Welcome to the fourth lecture of on Riemannian symmetric space. In previous lecture, we have defined something called pseudo-algebraic group. These are really basically the groups which are given by okay. So these are pseudo-algebraic groups are the groups which are really specified by certain polynomials. Okay. And we have seen that if G is a pseudo-algebraic group and any conjugate of that group is also a pseudo-algebraic group. So then finally we have proved a lemma which says that if Qt is a polynomial exponential, that means Qt is of the form Cj e to the power bjt, where Cj is a complex number and bj belongs to R. If that polynomial exponential vanishes at integers, then it is 0 for all t belongs to R. Okay, so this we have seen. So what we will do, we will actually use this lemma now, and we will today we will prove polar decomposition for pseudo-algebraic. Okay, so before I really introduce a notation, this is called a multi-index. If alpha, that means alpha belongs to n to the power n, alpha is equal to alpha 1, comma alpha 2, alpha n. And this alpha I belongs to natural number. Alpha I belongs to n. Okay. And this mod alpha is summation of this alpha 1 plus alpha 2 plus alpha n. Okay. So now onwards, actually, we will see that whatever I will teach, actually, it will be little it will be unfamiliar to most of you. So you have to really pay some attention here. Okay. So I will start with a lemma. Okay. So let G be a pseudo-algebraic group, and let H is equal to diagonal of H1, H2, Hn. This Hi belongs to R. Hi is a real number. So suppose so exponential of H, this belongs to G. Then conclusion is this thing: exponential of TH belongs to G, or all T belongs to R. Okay, so look at the lemma, statement of the lemma. It says that G is a pseudo-algebraic group and H is a diagonal element, where this diagonal entries belongs to real number. If exponential of H belongs to G, then exponential of TH belongs to G for all T belongs to R. Okay, so this is my lemma. I want to prove it, and we will use that polynomial exponential lemma. Okay, proof. So H is equal to diagonal of H1, H2, Hn. This Hi belongs to real R. What is the TH? TH will be something like diagonal of TH1, TH2, THN. Okay, so what will be exponential of TH? Simply this will be diagonal of e to the power TH1, TH2, e to the power THN. So what is the hypothesis? The hypothesis is exponential of H belongs to G. So exponential of H belongs to G by hypothesis. So that since these group, then this will imply that exponential H to the power K, this belongs to G. Okay. Now that thing is this will belong to K belong to J. First you take positive power, then you take the inverse, then you will get that exponential of h to the power k belongs to g for all k belongs to z. So this is same thing as exponential of kh. Okay. Now what is so exponential of kh is, if you will put t is equal to k here, this will imply diagonal of e to the power kh1, e to the power kh2, e to the power khn. This belongs to g. Okay, for k belongs to z. This is given, and we want to say that exponential of th. Our claim is that we want to show that this thing, this exponential of th, this belongs to z. Okay, now what I will do, I will write a statement. Listen to that statement carefully. If you understand, then it is good. If you don't understand, don't worry, I will clarify it. Okay, so what I'm saying, I will write a statement and listen to that statement carefully. Okay, so since G is pseudo-algebraic, G is given by some polynomial, so that means this e to the power kh1, if diagonal of e to the power kh1, e to the power kh2, e to the power khn belongs to G, then e to the power kh1, kh2 to the power khn, this satisfy some algebraic equation. K belongs to J. Okay. Now, by using the previous lemma, e to the power th1, th2, e to the power thn will satisfy same set of algebraic equation. This implies diagonal of e to the power th1, th2, thn, this belongs to G. Okay.
Can we just go back to the previous lemma?
ये polynomial exponential, yeah, this is the thing.
Polynomial exponential function. Now this.
Okay, I'm coming to it. Okay, so is this actually I have written this. I have not clarified it.
Okay.
If you have understood from this thing, then you have good maturity. Okay, what I'm saying. Okay, so and I will clarify this. Okay, so for t belongs to R, okay, and I don't expect that you will be able to do using this thing only. So clarification I will give now. So clarification is this is suppose you would first consider that suppose G is given by some single polynomial P. Given by a single polynomial P. Okay. So and what is in your hand is this is in, you know that. So we have that exponential of kh belongs to G or k belongs to J. This is we know, and we have to show that exponential of th. Sorry. This is equal to diagonal of e to the power th1, e to the power th2, and e to the power thn. This belongs to G. We have to show this. So this is need to show. Okay. Now this exponential of th has non-diagonal coordinates 0. And if you look at the diagonal element, it has only real coordinate. Okay, imaginary diagonal coordinates are 0, right? So for that reason, actually, first I will decompose this P. I would write this P is equal to P1 plus P2, where these P1, P2 are polynomials. Okay, and what is P2? P2 is that linear sum of linear combination of monomials which contains at least one non-diagonal coordinate or something like y1 or y22 or yn. Okay, so let us and whatever first I will choose P2, and whatever is remaining that will be P1. Precisely P1 will be my P minus P2. So let us give an example.
Now you said contains at least one non-diagonal coordinates or this.
Or y1, y2, yn.
That means
Non-diagonal
the
x1.
diagonal ones, right?
P2 is contains non-diagonal coordinate or imaginary.
Acha, by this we mean that imaginary ones.
Is by the y x11. I
Those
am
are
not.
real.
Yeah, example I am giving this thing. Suppose P is equal to say 3x11 y11 okay y22 plus so 4 x11 x22 x33 plus 6 x11 x22 x323 square minus 9c. Okay, this is the thing. Now if you take this thing, this actually this contains y1 y22. Okay, so this will belongs to P2, and here actually it do not have, and here actually this is a non-diagonal coordinate, so this will also P2, and whatever remaining is this P1. So P2 is equal to something like 3 x11 y11 y22 plus 6 x11 x22 x23 square, and what will be my P1? P1 is equal to 4 x11 x2 x22 x33 minus 9. Okay, so this is I hope this example is clear.
And these
So,
coefficients can be complex numbers also, right?
yeah, complex number. It isn't, you can put I also. Okay.
Okay.
So this thing, this example. Okay, so this is my example. Okay, so that means if you give the description of P1, then P1 will be explicitly polynomial in this the diagonal element, real diagonal element. So P1 is a polynomial. P1 is a polynomial in x11, x22, xn. This is clear. And P1, you can write this, that will be of the form some C alpha, where alpha is a multi-index. Actually, I have should have it. And okay, so let us. And mod alpha less than equal to some L. C alpha, x11 to the power alpha 1, x2 to the power alpha 2, xn to the power alpha. Is it clear, Manojda? P1 will be a polynomial in this thing. So far clear, right? Hello? Pritam, is it clear?
Yes.
Yeah. So P1 will be a polynomial in this thing. Okay. Now let us understand the meaning of this thing. So exponential of th belongs to g. You want to show this thing, right? What does it mean? That will imply this Same thing is diagonal of e to the power th1, e to the power th2, dot dot dot, e to the power thn. This will satisfy P. Okay. So this is, since this has non-diagonal coordinates 0 and imaginary diagonal coordinates are 0 of this matrix exponential of th. So this is equivalent to saying that diagonal of e to the power th1, e to the power th2, dot dot dot, e to the power thn will satisfy P1. Because P2 of, if you will put that P2 coordinates of this matrix, then P2 of that will be 0. Okay, so what is, okay, so remember this, okay, so remember this P1 of x is something like alpha belongs to n to the power n, C alpha x1 1 to the power alpha 1, x2 2 to the power alpha 2, into, okay, xn to the power alpha n. Okay, so let us put that it satisfies P1. That means alpha belongs to n to the power nn, mod alpha less than equal to m, C alpha e to the power t h1 to the power alpha 1 to the power t h2 to the power alpha 2 thn to the power alpha n. So let us erase this. This will be 0. So I hope you. So this will be alpha to the power n, C alpha e to the power t h1 alpha 1 plus h2 alpha 2 plus hn alpha n is equal to 0. Now, whatever this quantity, I will call this as B alpha. So,
Muna, can you just go back to the previous page for a second? I just lost my internet connection for some time. So, okay, these are your P1. So P1 you written like this. Yeah, then?
Yeah. Okay, P1 I written like this. Then I want to explain that what is the meaning of exponential of th belongs to g. Okay, since g is pseudo-algebraic and g is given by this polynomial p, I am this is equivalent to fact that diagonal of e to the power th1, e to the power th2, e to the power thn will satisfy p, right? Yeah. So, but the thing is, by construction, if you put this coordinate entries of that into p1 and p2, so that will give that p2 of that p2 of this matrix, that will be 0.
0, yeah. Because so P1 of that should be 0 also.
Now P1, this is equivalent to side with that. This will satisfy P1. Okay. And what is P1? This P1 is something like C alpha x1 1 to the power alpha 1 xn to the power alpha n. Yeah. Okay. Mod alpha less than. So I am putting that.
Okay. Okay.
X1 is e to the power th1 to the power alpha 1, e to the power th2 to the power alpha 2, e to the power thn into alpha n. And finally, I am getting this. Okay.
Okay. Thank you.
And what I am calling this element entry, this is B alpha. So B alpha is equal to H1 alpha 1 plus H2 alpha 2 plus Hn alpha n. Okay. So observe, since HIs are real, so B alpha belongs to R. Okay. Since HIs are real and alphas are real. So that will be alpha belongs to Nn, and okay, let us mod alpha less C alpha e to the power t B alpha, this is equal to 0. So this is same thing as Qt equal 0, where Qt is equal to, okay, T value. Okay, this is a polynomial exponential. So conclusion, conclusion, what I'm getting, this exponential of th belongs to G if and only if and only qt is equal to 0. Okay. Exponential of th belongs to G if and only qt is equal to 0. But we know that we have exponential of kh belongs to G. This is by height we are getting. Okay, we know that. Okay, we know. That implies this k belongs to Z. That implies this qk is equal to 0. K belongs to Z. This will imply that qt is equal to 0. T belongs to R by that lemma, by previous lemma. That implies exponential of th. This belongs to G. Okay, and this is what I wanted to prove. Okay, Preetham, is it okay? Clear? Yes, yes. Okay, so exponential of th belongs to G. I have taken that G is given by a single, specified by a single polynomial P, but you can apply the same argument to a set of polynomials, and you will get that exactly the same argument will give you the proof. So I hope this lemma is clear to you. So that G be a pseudo-algebraic group, and let H is a diagonal element. If exponential of H belongs to G, then exponential of TH belongs to G for all T belongs to R. So we have proved this. Yeah.
This will work only for finitely many polynomials, right?
No, in fact, you can take any set of polynomial.
For infinitely many?
Yes, you apply to the argument to each polynomial. So first you pick up a one polynomial, you pick any arbitrary polynomial, then actually you do the same argument.
Achha.
Do you get or do you need clarification?
No, I think it is enough to verify it for finitely many.
For one polynomial, it is enough.
Okay.
I can even if you want, I can modify the proof a little bit.
No, it's fine.
Okay. So now I want to prove the next lemma, and next lemma is the similar statement, but instead of a diagonal element, you take any element from the Hermitian matrix. Okay. So next lemma. So let G be a pseudo-algebraic group. Let H belongs to Hn, and let H be such that exponential of H belongs to G. Just wait, I will drink some water. Okay, let H belongs to Hn be such that exponential of G, then exponential of TH belongs to G for every T belongs to R. Okay, proof. So as H belongs to Hn, there exists U belongs to Un, so that U inverse is equal to H tilde, where H tilde is diagonal. diagonal of H1, H2, Hn. This is see, this is, since this is Hermitian, this Hi has to be real. Okay. Now you take U inverse is equal to H tilde. So that will imply that U inverse is equal to TH tilde. U exponential of TH U inverse is equal to exponential of TH tilde. Okay. So so hypothesis, exponential of H belongs to G. G is pseudo-algebraic. Now, but what is exponential of H? This is okay. This okay. Then exponential of H tilde. If you look at this equation star, this is something as U exponential of H U inverse. Exponential of H belongs to G. This belongs to U G U inverse. Okay. Now we have seen that this is pseudo-algebraic. Okay. Conjugate of a pseudo-algebraic group is, since U G U inverse is pseudo-algebraic, and H tilde is diagonal with real entries. Diagonal with real diagonal entries. So by previous lemma, you will get that X. Let us see. Okay, so by previous lemma, you will get exponential of TH tilde. This belongs to U G U inverse for U for T belongs to R. Okay. So now what is X? So you are getting that exponential of TH tilde belongs to U G U inverse or T belongs to R, and this is if you this from star, it is really U exponential of TH U inverse. So that will U exponential of TH U inverse U G inverse for T belongs to R. Then you cancel U and U inverse both sides, so that will give you exponential of TH belongs to G for every T belongs to R. So this finishes the proof of this lemma. Okay. So I hope this lemma is clear to you. So we are getting that exponential of TH belongs to G for every T belongs to R, and you will use this lemma in the next theorem, and this is the main theorem. So lemma is saying that let H be a pseudo-algebraic group and H is a Hermitian matrix such that exponential of H belongs to G, then exponential of TH belongs to G for every T belongs to R. Okay, we will use this lemma to prove the theorem. This is the main theorem and very useful theorem. So let G be a pseudo-algebraic group closed under conjugate transpose. So what does this mean? This means if A belongs to G, this implies A star belongs to G. Okay. So then G has the following polar decomposition. G you can write as G intersection UN into direct product G intersection PNC, and so you knew that exponential map also you want. So this will be e to the power Hn intersection G. Oh yes, G is the algebra of G. So these things are a homeomorphism. So I call this is okay. So let us. I call this is suppose y and this is 2y, and this thing is a homeomorphism. Okay, so G, so thus G is homeomorphic to okay, G is homeomorphic. Okay, so let us. Okay, so G is homeomorphic to G intersection union. Into R to the power D. D is equal to dimension of this is homeomorphism. Okay, the statement I think is clear to everybody. So G is a pseudo-algebraic group closed under conjugate transpose. Then G has the polar decomposition. G is equal to G intersection UN into G intersection PNC, and G intersection this is equal to G intersection UN cross e to the power Hn intersection G, where G is the Lie algebra of G, and this is the homeomorphism. G is equal to G intersection UN cross RD. I will give the proof. Proof let G is equal to UP. Okay, so okay, let G belongs to G. So since G is pseudo-algebraic group, so by definition it is a subgroup of GL and C. This implies G is equal to UP for some unique U belongs to UN and P belongs to PNC. This follows from the polar decomposition of G and C. Now, if I want to prove one, so I need to so look at the statement of one I. So I need to show that if to show one, I need to show that U belongs to G and P belongs to G. If I can show this U belongs to G and P belongs to G, then this will prove 1. Okay. So let us erase this thing. So claim U belongs to G and P belongs to G. Okay. So G is equal to UP. So okay, by hypothesis, G star is equal to P. Okay, P star U star, and this is U star. And G belongs to G. This G star belongs to G by hypothesis. because this group is closed under conjugate transformation. So that means G star G, if I will take, this will be P square, this will be belongs to G, as G is a group. Now as G star G belongs to PNC, this will imply that there exists unique H belongs to Hermitian matrix, so that exponential of H belongs to G. Okay, exponential of H is equal to G star G, and G star G is belongs to G. Okay, so this belongs to G. Okay, now G is pseudo-algebraic and H is Hermitian, so that exponential of H belongs to G. So now, by previous lemma, exponential of TH, this belongs to G for every T belongs to R. And I will put T is equal to half. So this will imply, in particular, this element H by 2 belongs to G. But this P is the square root of G star G. If you remember the proof that P has to be exponential of H by 2. But P is equal to exponential of H by 2, because P is a square root, unique positive square root of G star G. So, but P is equal to exponential 2. This implies P belongs to G. Okay. Now, if P belongs to G, then it is obvious that U belongs to G. But because since we have G is equal to UP, right? So since but U is equal to GP inverse, and P belongs to G, G belongs to G, so this belongs to G. So I have proved that P belongs to G and U belongs to G. So that means I have proved the first thing. Okay. And polar decomposition I have proved, but the restriction of homeomorphism is homeomorphism. For that reason, that this is homeomorphism. Okay. So let us write that. So the map G going to U plus P is UP is a homeomorphism from G to G intersection UN cross G intersection PNC. Is there any doubt? Or Pritam, is it clear?
Yes.
So this is clear. And second thing, actually, you have to really prove that these two things are same. E to the power Hn intersection G is equal to G intersection PNC. Okay.
So what are the examples of such algebraic groups which are?
Okay. I will see that. We will see that. But we have not completed the proof. Okay. So really, okay. So for second part, I want to claim this thing. Claim e to the power Hn intersection G is equal to G intersection PNC. One thing is very clear. One side is very clear. Clearly, e to the power Hn intersection G, this is contained inside G intersection PNC. Okay, because exponentials lands takes the Lie group, Lie algebra element to the group, and we have shown that exponential maps Hn to PNC. So this clear thing is clear, and we need to prove that converse thing. So conversely, okay, so let G belongs to G intersection PNC. Okay. Now, as G belongs to PNC, so that implies there is just a unique H belongs to Hn, so that exponential of H is equal to G. Okay, but this G is equal to belongs to G, and G is pseudo-algebraic. Now I can, and H is a Hermitian element, so I can apply the previous lemma. By previous lemma, you will get that exponential of TH belongs to G for all T belongs to R. Okay, so that means this is precisely the this says precisely that H belongs to the Lie algebra of G. I have H belongs to Hn here and H belongs to G here. That implies H belongs to Hn intersection G. Now this G is equal to exponential of H. This belongs to e to the power Hn intersection G. Okay, so what I am getting? I am getting G intersection P and C is subset of e to the power Hn intersection G. Yeah, let us call this star, double star, from star and double star. Above we get e to the power Hn intersection G is equal to G intersection P and C. So exponential map on Hn is a homeomorphism. So for that reason, this second thing is also homeomorphism. And so also if I prove this second thing, then I have shown you the argument. Then G is actually homomorphic to G intersection UN cross R to the power D. So this finishes the proof of this theorem. So this finishes the proof. So clear. It is clear. It is also clear that. Okay, let us write the one line. Like that. G is equal to homomorphic to G intersection UN plus R to the power D, where D is equal to dimension of. Okay. Now this finishes this lemma. Now this is a very useful lemma, because whatever classical Lie group you will see, that this will fall into that category. So you will use this lemma to find that find the number of connected groups of a group G, and whether the group is simply connected or not, you can also find. So corollary, one corollary I want to add: if G satisfies the hypothesis of previous theorem, so number of connected components of G equal to number of connected components of G intersection UN. Okay, so you will apply this result to various groups to get some interesting result. Okay, so now I want to define some classical Lie rules now. Okay, so I hope you know the definition of bilinear form and non-degenerate bilinear form. Okay, so let V be finite dimensional vector space over K, where K is equal to either R or C. So let B be a non-degenerate bilinear form on V. So I define this automorphism of B. So T belongs to B, so that T is endomorphism on B, so that B of TU TB, this is equal to B of U comma B for all UB belongs to B. Now exercise, or you might be knowing this thing. So what B is a subgroup of GL KB. This is members of this OT B are really invertible, and this OT B actually forms a group. Okay, so and another thing is suppose. Okay, so another exercise I want to give. Suppose V1, V2, Vn is a basis of V. Okay. Then T belongs to odd P if and only if B of TBI okay, so T of Vi, T of Vj, this is equal to B of Vi Vj. Okay, so I J when and okay, so this is this says that definition says that B of TU TB is from is equal to B of UB for all U and B. Just 1 second. One call is coming. I just. Okay. So if and only if this B of TBI or TBJ is equal to B of BIBJ, this automorphism of B actually includes that the B of TU TB is equal to B of UB for all U comma B belongs to B. But here actually I am taking this some basis element. Okay, and to so that hint as use bilinearity of B and linearity of T.
Muna, I have a confusion here.
Yeah.
For complex vector spaces, your B is linear in both coordinates, right?
Yeah, complex. Actually, I am not defined this as linear. That will come sexilinear form. This is for bilinear form. Okay, so yeah, is there anybody who doesn't know definition of bilinear form, or something like that, or I can assume that? Okay, let's. These are okay. So use bilinearity of B and linearity of T. Okay. So suppose now I will come back to this thing. Okay, suppose Okay, B is a bilinear polynomial B. On B, I fix a basis B1, B2, Bn, P of X is okay. So I am calling this a S, fix a basis S. Actually, I will not use this B. Actually, fix a basis S is equal to B1, B2, Bn. So I define a matrix. Let Aij. This is B of Vi, Vj. I define a matrix A with respect to this binary form B, AB. This is Aij. Okay, so now if I will fix a basis S, then B is actually isomorphic to some Kn, and I can you can check that B of UB, and this will be this U S transpose this matrix AB and B S, where this US is nothing but the representation of U in this basis S. Okay, so what I'm saying that you take U, B is a bilinear form on B. I fix a basis S is equal to B1, B2, Bn. So that means that will give me an isomorphism B to Kn. So any element U can be written as some element of K to the power n. That is precisely the matrix representation of U with respect to this basis. Yes, you can check that B of U B is equal to this. Okay, and another thing, now since I have fixed a basis, so I can look this group automorphism of B. Okay, inside some the group of MNC. Okay, and so this automorphism of SB actually, if I can write that T belongs to, you can check that this is nothing but MNC, so that T transpose ABT is equal to your AB. So, and this actually matrix representative depends upon the basis S. Okay, so therefore I am writing this is S. Okay, so and I have told you that this is, any element of belongs to automorphism of B is an invertible element. So I will get T belongs to, this is same thing as T belongs to GL and C. So that T transpose AB T is equal to AB. Okay. So now the thing is, from this description, you see that this is actually, since this matrix multiplication is a polynomial function, from this description, you see that clearly automorphism SB is a pseudo-algebraic group. Okay, because they satisfy some polynomial. Okay, so if you look at this thing, then you can again I will give you an exercise. Okay, suppose if small ot SB is the Lie algebra of SB, then small ot SB is actually I will okay, so let us write as this is equal to X belongs to MNC, so that X transpose AB plus ABX, this is equal to 0. This you can verify just simply differentiation. So I will actually drop always the subscript S unless it is needed. Okay. So this is so I am saying that automorphism of BS is a pseudo-algebraic group, and this is the Lie algebra. So now you want to really give some important example of classical Lie groups.
No, you can drop this subscript S, I think, right? If you take another basis, so it will be composing by some other matrix. Yes, so
yeah, conjugate. Actually, this is a very important point. Actually, for this reason, actually, let us here actually keep it as there are some subtleties there. Actually, you will see later. Okay. Yeah, if it is true that if you change this basis S to S prime, then you will get a conjugate of this thing. Okay. But for clarification in the beginning, I have written that auto SB. That's all. Okay, so examples of this thing. Okay, so first thing actually I will take this so-called OP, Q. This is called pseudo-orthogonal group. Group of signature P, Q. So what is the bilinear form? B of, okay, so this is a vector space. What is the vector space? B is equal to Rp plus Q, and X belongs to, take X belongs to Rp plus Q, Y belongs to Rp plus Q. So I should, okay, B of Xy, X1, Y1 plus X2, Y2 plus this XP, YP minus XP plus 1, YP plus 1. This will be minus X plus P plus Q, YP plus Q. Yeah, if you recall, what is the matrix here actually? The matrix will be so like the matrix corresponding to the bilinear form. One is IPQ, where IPQ will be, this is I P plus P matrix and minus I Q plus Q. This is 0, 0. So this is
canonical basis.
Actually standard basis. Yeah, I am fixing this standard basis here. Everything actually I will talk about the standard basis, but one case I will discuss about something non-standard basis, but because of some conceptual clarification. These are everything actually I am doing in the standard basis. Okay, so what will be OPQ then? So OPQ is, this is A belongs to MP plus QC. Okay, so that A transpose IP Q A is equal to your IP comma Q. So, and one can here replace that MP plus QC by GLP plus QC, but I have, but I am writing MP plus QC. I have some plan. So this is the thing. Now, if you observe that if OP0 is your OP and O0Q is your OQ. These are nothing but orthogonal groups. So, and this OP1 is called Lorentz group, and this is this group is really important in relativity. Okay, so And this B is a, this is a, you can check that non-degenerate. Non-degenerate is clear because this matrix IP, Q is invertible. You can check that this is a non-degenerate. Non-degenerate is clear. So non-degenerate and symmetric. Okay. So first example is good. Second thing. The second is I will take this ONC. ONC is, you know that. So P is equal to Cn, and this bilinear form is P of ZW is Z1 W1 to W2 Zn Wn. Okay, this is called complex orthogonal group. Complex orthogonal group. And this matrix is associated matrix is identity. You can see this by associated matrix to be identity. To B is equal to identity, and O C we can write that A belongs to M and C. So that this is a complex thing, not real, right? Transpose A is equal to identity. Okay, so this is complex orthogonal group. Third is SP to NR. This is called real actually non-symplectic group. So actually there are many symplectic groups. So when there will be some confusion, then you call this is real non-compact symplectic group. Real and non-compact. You will see that it is non-compact. For that reason, it is, and since it is contains real matrices, so that for that reason it is called a real non-compact symplectic group. And for actually we will write 2n, but some books also write SP n, R. For that reason, there are some confusions. Okay. So okay, so let us yeah. So let U prime V prime belongs to Rn. So you define B U V U prime B prime. This is dot product of U and B prime minus B dot U prime. Okay, so okay, let us see. Okay. So B of U V U prime B prime to U V dot B prime minus B dot U prime, and associated matrix is Z tilde. I call that, if you calculate what is the matrix, this will be 0I minus I0. And this is equal to minus, so let us write. So Z tilde is equal to 0I minus I0. So this is the same thing as minus 0 minus I0. And this is equal to minus J. If you remember, this J is the standard complex structure in the Rn, where J is the standard complex structure on R2n. Okay, so what we'll get that SP 2nr is equal to A belongs to M2nr, so that A transpose J tilde A is equal to J tilde. But since J tilde is equal to minus J, so you can also write that this is M2nr, so that A transpose J is equal to J. So this is the symplectic group, non-compact real symplectic group. So similarly, we can define this as something. Okay, IB sp2nc. So you define the same thing. B. So this is complex symplectic group. So this you take this B Z W Z prime W prime. This is Z dot W prime. You define analogously to. So here Z belongs to Cn, W belongs to Cn, Z prime belongs to Cn, W prime belongs to Cn. Okay, so this. So similarly, here the matrix is also Z tilde. Here associated matrix is Z tilde. This is called minus J. Okay, so SP to NC. This is M to N. M to NC. So that A transpose Z tilde A is equal to Z tilde. And you can write that A belongs to M to NC. So that A transpose J is equal to J. Okay, this is the complex symplectic group. Okay, now actually I want to give an important exercise. Okay, so definition. Actually, this definition is very. You should not worry about means. Actually, definition of classical group. Actually, I could not find in any group book. Actually, what people do that they write a section on classical group, and they produce the example. Actually, I found this definition in the Wikipedia, so I am giving this definition. Actually, this name classical group sort of comes from physics, because physics people actually use this group. Actually, these are important for some physics people actually. Okay. And this so-called symplectic group, actually this sp2nr, this is actually important for the point of something called symplectic geometry. It is very important group actually, sp2nr. So I am just definition of giving the definition of classical group, but we will see some a group.
Muna,
Yes, sir.
Chevalier calls them classical groups.
Yes.
Chevalier.
Yes. Yes, sir.
Yeah. So that's why we also call classical groups.
Okay, sir. Thanks. So this is the Wikipedia definition. A group G is called classical Lie group if it preserves a bilinear form, bilinear or sesquilinear form. I will define this sesquilinear form later. Form on a finite dimensional vector space over R, C or H. This is called quaternions. Okay. H is quaternion. This is the skew field of quaternion. Actually, we will see that this later. Okay, so this is the thing about. Okay, all these groups are classical Lie groups. These examples.
But that means that they are algebraic groups, right?
Actually, I do not know algebraic group definition.
No, your definition of pseudo-algebraic. If you take
that means yeah, pseudo-algebraic group. That is O, P, Q, and U. Sorry, we will see more example later. sp2nr, sp2nc, onc. Okay, so later. Now I will give an important and conceptual exercise. So okay, so and I will want this exercise to think, and then we will discuss this exercise. So okay, so let B is equal to C P plus Q. Okay, and I define this. Let Z W belongs to C plus P plus Q. I define this thing BZW. This is equal to Z1 W1, Z2 W2 plus ZP WP minus ZP plus 1 WP plus 1 minus ZP plus Q WP plus Q. And this is a okay. This is a bilinear form, and the associated matrix is something like it is the same I P comma Q. Okay? And I can define this thing OPQC is the A belongs to M and C, so that A transpose I.
there will be some minus sign, right? I'm not making any mistake.
Where?
There's some minus, right?
I have written minus.
No. This IPQ. What is the meaning there?
Okay, IPQ I defined, right?
Okay. So first first P coordinates are 1. Oh.
1, and this is the same. This is diagonal of, so diagonal of 1, 1, 1. This P times.
And then minus 1.
So minus 1. This is 4 times.
Okay, sorry.
Okay, that's okay. So Q times. So this is equal to IP comma Q. Okay, so this since IP comma Q is invertible, this is a non-degenerate binary form, non-degenerate and symmetric. Okay, so I will really, and this OPQC is a group, but in books actually you will not find the definition of OP comma QC. People usually do not define it, and what is the reason for that? So in literature, in books, actually I am writing this thing, but you will make it. You don't see OP. You don't see OP comma QC. This thing. What is the reason for that? This is a very simple question, but related to total bilinear form. So we will answer this thing in the next slide. So this is an exercise. So I have 3 minutes. Okay, I have finished, I think. So next lecture, then I will start this OPQ comma Q. So is there any question?
I'm gonna give some non-trivial pseudo-algebraic group. Can you give some?
Actually, these are the groups actually OPQ, SUP.
These are the. I mean, there should be something else, or is it, or they are all?
I do not know actually. Pseudo-algebraic group. Actually, I have taken that definition from this book called Helgason,
Okay.
and in there actually, if he proves that statement, then you will see that using that theorem which we proved today, then you can get all these topological properties of this thing. Actually, these are very important for the classification of symmetric space. Actually, you have given complete classification of symmetric space, and usually use this precisely these groups which we will discuss about.
For polar decomposition to be true, we also need them to be closed under conjugate transpose, right?
Yeah, you will see that the group which we will discuss about will say that it will have those properties. Yeah, you can take. Okay, I taking this clue actually. No, actually I don't think that I will. Apart from these groups and orthogonal groups, SUP Q, UP, Q, those groups which I know, I cannot really produce some weird example of pseudo-algebra.
Oh, this is fine. Okay.
Okay, is there any question? Okay. So it's good to see that Mughaldam sir is here. So he is an expert in this thing.
I just wanted to say, Mona, there is a book by Winberg.